Good evening. We are going to talk about elliptic PDEs, Lax-Milgram theorem, Galerkin method in the field of neutronics. I will be helped by a book, Mathematics Methods in Neutronics by Jacques Blanchard, and especially the second chapter. Neutronics is the field of studying neutron flow. So the physical quantity called neutronic fluence, so fluence neutronique, which is the flow of neutrons, and translated to mathematical problems, and that's the topic of this book. In particular, the second chapter is talking about the introduction from a easy undergrad point to a more advanced point. So I thought it was interesting to make a video about it because there are some very interesting aspects that I really liked. So PDE in neutronics, how does it work? So we will start with a one-dimensional single group of energy diffusion equation without delayed neutrons. So here we have a term that you might be common with, a term with that resembles a diffusion law, so with a diffusion coefficient and a gradient of a quantity, and this variable we take the divergence because we will integrate it in a certain domain, plus a term that is linearly dependent of sigma of phi, and a source term. So here we are solving for phi, the neutronics flow, so fluence neutronics. It's the whole point of the field. The whole point of neutronics is to calculate phi. The second thing is the diffusion. So it's a diffusion coefficient in which you can find in a Fourier law or any law that involves a coefficient times a gradient. And then you add with this coefficient a coefficient of absorption. So in neutronics we consider a variable called cross section, which is the equivalent of probability with if I say so myself, it represents the probability that the neutron will be absorbed. So here is the regular flow of the neutron, the probability that it will be absorbed, and a source term if you have a radionuclide emitting some neutrons. And just as a quick reminder, the fluence neutronique represents a density of neutrons times the speed for its group of energy. And here, so how does it work? So neutrons in a reactor can have multiple energies, so multiple speed, and we usually split them by speed. And obviously, it's a continuous variable, so it's very hard to make groups. Currently, people use more than 2,000 or 4,000 now groups of energy, so they split in small intervals of energy, so between 0 and 1, between 1 and 2, etc. But here we will consider the case of a single group of energy, but just by averaging the speed. It's not really a problem because we can extend it to any group of energy, but for this presentation it's fine. And delayed neutron is an effect that is problematic for this PDE, but I'm not going to talk about it. So boundary condition, so the PDE presented earlier is not perfectly described as it needs to have boundary conditions. So the first one is that the flow on the surface, on the exterior surface called gamma, here we'll call gamma the external surface, will have no leakage, so no neutron will leave the reactor. It's called the Dirichlet condition, or Dirichlet. I've heard some teachers say Dirichlet, but I'm pretty sure it's wrong. Dirichlet, Dirichlet. I don't know. So this represents the fact that no neutron will leave the reactor. The second one is called, it has actually no conventional name. In French, we call it either condition Fourier, so Fourier condition, or albedo condition, condition albedo. It represents the fact that in reality, what hits the water outside the reactor is partially neutrons. So you have to consider the fact that a small portion of neutron escapes the reactor, else it will lead to like a bomb. So the number of neutrons would increase if you have a source term, and you need to have some kind of small leakage represented by a coefficient alpha here. It just means that a small portion of the flow goes to the exterior of the reactor, and it's actually more representative of a real system than this that is way too perfect. And one can show that if you put alpha to plus infinity, you will actually find back the Dirichlet method, the Dirichlet condition. The third one is called the Neumann or von Neumann condition that we often use in symmetry planes because the reactors have high number of symmetry, and usually we use this condition that I did not explain the partial over n. N means the normal to gamma. So when you do your integral over a boundary, you have an integral, your gradient, you put it into the normal of the boundary. So here the derivative to the normal, so the derivative of the flow that goes to the exterior is 0. Because obviously, this can be really obvious if you have something that is symmetric. If you have a positive of this, it means that if you consider the left, it means that you will have more you will have more neutrons that leave 1 to 2 to the sector 2 than from 2 that goes to the 1. However, by symmetry, it should be the same for 2. There should be more that goes outside than inside. But it's contradictory with the fact that it's symmetric, so we can't have if you have on the left, imagine on the left a reactor 1 and on the right a reactor 2. If the 1 is 0, it means that they are both at equilibrium of neutrons. So if one goes back. And if you have a positive, it means that the derivative through the normal is positive, which means that the flow goes in a certain way. So 1 emits more than it receives. However, by symmetry, the same thing should apply to the other one, which would give more neutrons to the sector 1. But it's not possible because you can't say that 1 gives more to 2 and that 2 gives more to 1, because it's a net exchange. You can't have like this condition. So this reflects the symmetry aspect of the boundary condition. So I list them, but I'm not saying we use them all at once, or it depends on the geometry, but it's just to present them. So here we have our equation with our source term. We consider the one-dimensional aspect. I will drop the gradient after, so I will just put grad because I was lazy to type nabla and the vector. And omega will represent the inside of our reactor, and gamma will represent the outside the boundary. And here we will consider a Dirichlet condition in which u of x is equal to 0. If you ask why we pick u instead of phi, it's because it's easier to write. Actually, the book also uses the same notation. So let's use that, because to write phi is harder than to write u. Okay. Okay, so now we will define what's an elliptic equation. So you have this equation that is just the definition. We'll multiply with v, a function nice enough. So by nice enough, I mean that it's continuously derivative, that's, how do we say it? It's d2, so the derivative is continuous on all the plane, so it's not like derivative once and derivative at another place, and then by continuity you make up a limit, you make up a function. It means that it should be continuous twice. The derivative should be continuous twice. So it's continuous, the derivative is continuous, and the second derivative is continuous, and not continuous by parts, but continuous always on the inside, so the inside omega. And v on the boundary should be equal to 0. So we have this equation, we multiply by v of x, and we integrate over omega. So this holds. Now we'll use an identity. I think it's called green identity. Yeah, something like that. So it's an identity of the divergence operator, in which you can split when you have this sort of problem, and you have a term that is a product of two gradients and a product that is on the boundary gamma. Now we have this junk. So for a Dirichlet condition, obviously, if u is equal to 0 at the boundary, the derivative to the n is equal to 0. So all this junk disappears. If you have a von Neumann condition, this also disappears, because we said the derivative of u over n was equal to 0. And if you have a condition Fourier, you have to have a certain term added to it. So it's nice because we have a form that is something that is static, so something that will not move, and something that will depend only on the conditions, that we could add like kinda as a source term. So you see that our source term is here, and just by putting it to the other side, we can have it quickly. However, it's not the method we're going to use, it's just to explain the method. So yeah, with Dirichlet, the term depending on gamma disappears, on the gamma disappears, because here we expanded this part and not this part, and we get this junk. So we define a new function, actually a new operator that depends on two functions, u that is the neutronic flow, and v that is called a test function that is d2 on omega, and that is equal to 0 on gamma. So we have our operator a that is defined as this, and for the case of Dirichlet condition, it's equal to this. Now, what if we take the von Neumann limit? So we also see that this term disappears, which is nice, and we always find the condition that a of uv is equal to f of the integral over omega, that f times v dx. And for the albedo condition, this time we have to use another term that comes from just the definition, that makes the appearance of a factor alpha compared to previously. And obviously, now we get that a of uv with this new term on the albedo condition is equal to the integral of fv dx on omega. So now we'll consider the variational equivalent. So we have a problem that is that the operator a applied in u is equal to f. We have a part of the boundary condition called gamma 0, in which the Dirichlet condition applies, in which the neutronic flow is equal to 0, and then another part called gamma 1, in which the Fourier condition holds. And this is equivalent to finding U in the space of V, such that this. And here we have explained, we have a term in which we have two parts, and actually only the parts in gamma 1 matters. And this must be true for all V. And this is the product, how do you say, the scalar product. Yeah. And V represents the closed subspace, so H01 of omega, in the space of Sobolev H1 of omega, with functions V whose trace is 0 on gamma 0. So I actually don't know why the fact that the trace is 0 needs to be it, but let's assume it's the case, because I don't want to have problems in which something diverges and you can't prove that the solution exists. So we'll define two conditions, 1 and 2. The first one is that the function is bounded by u and v and a constant. So that's the first condition that needs to be done. And the second one is called the coercitivity or coercive, and it's a condition in which the fact that you apply it in two test functions, it must be above v squared. So this is used in the theorem we'll use later, and in practical case it's almost always the case. Like if you don't have a function going to infinity or things like that, it should often be the case. In particular, if you have this set of equations, so if d of x is between c and d0 positive, and c sigma, so the cross-section of absorption is between sigma 0 and c on omega, obviously, then 1 and 2 are both true if you pick alpha to be equal to the minimum between d0 and sigma 0. Okay. I will not prove this, but just say it is the case. You can also prove by yourself, by the way. Okay, so now we'll get to our first theorem. So the theorem of weak compacity. Let g of k be a sequence of function in L2, so the usual L2 space, such that gk is bounded absolutely with c a constant independent of k. Then there exists j star in L2, obviously, and a subset sequence gk prime extracted from gk, so that it converges, so that gk converges to g star. And this will be quite useful, because here we'll use it on the operator a, and we will use a sequence um prime, and it will converge to a function u. And the function v, as we said earlier, it must hold for all function v, so it doesn't matter what's h or what's v. They are called test function. Their value does not matter. And we will approximate our neutronic flow as a sum, so as a infinite sum of alpha I times Vj. So there must be some reason why we can do that, but I'm not sure why exactly, but we can. And then we'll limit it to an order m in order to have a linear system. So we have u that can be expressed as a sum of Vj, and Vj will represent a convergence aspect. So we have test functions that will index them with this. So instead of having one test function v, we have m test function v. Oh, and also this should be a j, alpha j here. wait. Yeah, it should be alpha j vj, and here it should be, wait, what? Where is my book? Wait, hold on a sec. Okay, so I checked, and it's alpha j vj and alpha j vj. So it's a bit problematic because vj are test functions, so they can be anything, and alpha j are coefficients that are really hard to find because this is a function and this is a function. But we'll just assume this approximation because in practice it works well because we are dealing with programs, with computer science, and computer scientists, they like when you can approximate something, so it's cool. Approximation, and now, so here we have our operator A that is now on the function Vj, and we will have as a sum of alpha I because of this, of the thing above, because of this, and it will be equal to the scalar between f and vj, and for all j from 1 to m, and m will represent our convergence. So every time m increases, our um will converge to a certain neutronic fluence. Vj will change slightly, and our sum will increase and have a new term, and our new term here will be recalculated every time. So as we advance in our problem, we find a convergence of our flow, of our fluence. And now you will notice that if we sum all of this over j, the sum will go inside in the j part, and it will be actually this. Sum of if we sum times, I forgot the alpha j times a of vj. The sum of j alpha j can be put inside by linearity, and you find the um because this with the alpha j goes inside, and you have a final problem here in which you have a that will converge to a certain value. And with the coercivity that is guaranteed by this, we show that the sequence converges to a solution. It's called the Galerkin method, and in general for all PDE it's called the Theorem of Lax-Milgram. So in French it's called the Theorem de Lax-Milgram, but in English it's called the Lions Lax Milgram theorem, and which is strange because Lyons is French, so it should I don't get it. So let's look at what Wikipedia says about this theorem. Let H be let H be a Hilbert space and V a norm space. Let B be a function, so the space of function that goes from H times V to R. So here it will represent the space of our function A, which is A of U times V, to R, to be a continuous bilinear function. And it is the case. Then the following are equivalent. So the condition of coercivity for some constant positive. So it's a bit of junk, but basically we say that it's bounded by a constant c, so the constant coercivity, and the existence of a weak inverse for each continuous linear functional f. There is an element h inside big H, such that b of hv is equal to the scalar product of f times v for all v. And in particular for the case of Neutronics, so this equation has a unique solution in the closed subspace of the subrolette space of omega when the coefficients d and omega satisfy these inequalities. Now we can move on to variational calculus. So what computer scientists like is do a gradient descent. They love this. It's amazing. They really love it. So let's turn our PDE problem into a variational calculus problem. So here we will build a function j that will be the difference between avv and minus 2 times the integral of av dv f v dx on omega, and j will be called the quadratic functional related to v, and in particular, if you differentiate it, apply the u plus tv in 0, you will it will be equal to 0. So once again, you find a variational problem, a problem of gradient descent. So you descend from this to find a 0, so a minimum. So when you will find this minimum, you will find the value u, and u will represent the neutronic flow at convergence. And obviously you can define stuff like green function and green green kernel, and you can apply lots of variational calculus tools to this problem. And these aspects are explained more in other chapters of the book. So this concludes my presentation. Thank you for watching, and goodbye.